Okay, great. Thank you very much for the introduction. Okay, so our work is generally situated in the area of VR AR telepresence. So the idea here is that VR users will virtually enter the physical space of an AR user. And for presenting that physical environment to the VR user, past research has identified trade-offs between rendering depth-based reconstructions, as you can see on the left, and 360-degree video, as you can see on the right. So reconstructed environments, such as point clouds, allow users to virtually move around the space and interact with the scene with full kind of depth perception, but those depth-based reconstructions can suffer from artifacts such as occlusion and holes. By comparison, 360-degree video delivers a virtual scene with higher visual fidelity, but also typically provides less interactivity and less freedom of movement. So in past work, to try to improve the interactivity of 360-degree telepresence, prior work has implemented basic interactive modalities, such as pointers and annotations. Or, for example, to improve the freedom of movement aspect of 360 video, have provided things like locomotive robots to enable motion, but of course this requires quite a bit of dedicated hardware. Another option implemented in past work is to allow users to toggle between a high-resolution 360 video and an interactive depth map. But unfortunately, as you can see in this video, this results in high context switching costs as you have to constantly switch between those different environments. So in this work, we present VirtualNexus, which is a system that enhances the interactivity of 360-degree AR-VR collaboration and telepresence. And concretely, we contribute coherent interactions that mix depth reconstructions and 360-degree video without the need for context switching. We improve access to the remote environment using something we call environment cutouts. And we enable digitization of physical objects using 3D replicas with a lightweight scanning mechanism. Okay, so to start with, let's look at a video of how VirtualNexus works. And it's important to note that we're just using totally off-the-shelf hardware here. Right? So VirtualNexus is supporting a local AR user and a remote VR user to collaborate in a telepresent experience. In the physical environment, we have a 360-degree camera, which we align using a QR code, implemented basic functionalities such as synchronized annotations and shared virtual objects. Now, we further enhanced remote telepresence with environment cutouts. And so here, the VR user defines an environment cutout by selecting some points and bringing that part of the world towards them. As they pull the world towards them, the AR user sees the VR user move towards that whiteboard. And this provides spatial awareness and collaborative awareness. The VR user simultaneously will get a close-up video of the area of interest, allowing for more precise work. Okay. So after they sketch this bar graph on the whiteboard, the users then decide they want to visualize the bar graph in a bit more interactive way. So we cut out the desk here, so we can build the bar graph in 3D on the desk. So the VR user pulls this out, and both users create a 3D visualization just using the virtual primitives. And in the meantime, if the AR user wants to scan physical objects to create virtual replicas, they can do that by walking around the object, doing a quick scan of it with the forward-facing camera, and then those become shared virtual objects that they can spawn from a menu. Here, they use the virtual replicas just as legends on this 3D bar graph. Okay, so the general architecture of VirtualNexus is as follows. On the AR side, the local user is wearing a HoloLens, and it streams the environment using an Insta360 camera. On the VR side, the remote user wears a MetaQuest headset. On the video side of things, we stream the 360-degree video in real time, synchronizing the VR head positions and controller positions to create the avatars. And then for the virtual replicas, there's a separate pipeline where the AR headset sends the RGB-D, so this is RGB plus depth images of the object, scanned by the local AR user into the virtual replica server. And that server then creates meshes that are sent to both the AR and the VR side. And then finally, using Unity mirroring, our system synchronizes those virtual objects, those annotations, and the spatial mesh using a peer-to-peer setup. Okay. So VirtualNexus addresses the three challenges. We'll dive a little bit into the implementation here. So that first challenge is to ensure that coherent interactive experience using the merits of both 360-degree video and depth-based reconstruction. So what we're doing here is we embed and align an invisible spatial mesh with the 360-degree video. So we get the spatial mesh off of the HoloLens, which defines the spatial mesh of the surroundings. We embed that with the 360 video, and then virtual objects that are spawned onto the 360-degree video background by either user will obey physics according to the spatial mesh. In order to create a coherent experience, we actually render that 360 video monocularly, as well as any objects that are placed in the background, so that they appear as if they're part of the 360 video, but they obey physics as if they were part of the depth reconstruction. Okay? So as the main medium of delivery, that's kind of background view, the 360-degree video provides a high-resolution view, while the embedded reconstruction provides that illusion of physical presence and physical interaction. Next, to address the issue of the fixed point of view, so our camera doesn't move, which gives the VR user a fixed point of view in the 360 video. But to address this challenge and enable mobility, we provide users the ability to create these cutouts. So instead of having users walk around the scene in VR, the users bring parts of the scene to them. And the way they do this is they pick 4 points to find a bounding frustrum for the area that they're interested in. We intersect that bounding frustrum with the spatial mesh, and then we texture and render the spatial mesh using the 360-degree video. This creates the environment cutout. And the users can then reposition this cutout arbitrarily, and we track that position, and we render that as a positional change for their AR avatar. So in AR, their hand and face are their hands and face are always going to be relative to that cutout, as well as the gaze position that they use in VR. So this way, we give the AR user a perfect view of where the VR user's focus is and what they're interacting with. Okay. The environment cutouts also function as synchronized worlds in miniature. So manipulations on those components are then synchronized to the original scene in VR, as well as to the remote user. So basically, any annotations, for example, that we do here, or any objects that are spawned, are visible in both the 360 video as monocular video in the background, as well as visible to the AR user in their overlay. Next, what we have is the final challenge that we tackle is the lack of access to remote physical objects. VirtualNexus allows the AR user to easily scan in objects and using the AR headset, which generates a textured mesh that both users can interact with. So concretely, the way this works is we first take the user first centers the original object in their field of view and then walks around it to scan it. We then perform background segmentation of the images from that scanned video. And so we're using a combination of planar ransack, so we're detecting basically any sort of plane that it sits on, using ransack to detect the exact position of that plane, and then using the depth map to cut off that object. And then simultaneously, we're also using segment anywhere to obtain a mask of the object for better refinement. We then intersect the two masks that we get, pick the largest overlap for the segment anywhere hierarchy, and use that as the mask for identifying the object in the space. Then we use instant NGP to create a volume rendering of that object from those photos and corresponding camera poses. So instant NGP basically kicks out a volume rendering using a neural radiance model. From that neural radiance model, we mesh the object using cube marching, and then specifically also preserve the vertex colors. And then finally, to improve the appearance, we smooth the whole mesh with voxelization, removing artifacts, and also reducing the polygon count. Okay, so this process allows the AR user to kind of automatically insert physical objects into the virtual collaboration. Okay, so here's a couple of example application scenarios. In this first example, we show how users can collaboratively prototype a virtual scene with VirtualNexus. So the two users use preloaded primitives and scanned objects to create a scene where the characters travel through a forest. In this next example, VirtualNexus can be used for remote education and instruction. So we show how a remote user can go close to a whiteboard in order to answer a math question with annotation. And then also, the instructor can create virtual replicas of physical items and ask the learner to follow along with their instructions. And finally, we can use it for shared recreational activities. And so here we show a pair of users using their floor as a bowling alley with fully rendered physics. Okay, so to test the performance of VirtualNexus for collaborative tasks, we evaluated our system with 7 pairs of participants who collaboratively designed and prototyped a storyboard for a researcher-provided narrative. Participants discussed and ideated the storyboard through cutouts and annotations, and then they created it using virtual objects and replicas. So some sample storyboards can be shown on the right. After they completed that task, the participants answered some Likert scale questions about the system's effectiveness, immersion, and how participants perceived each other's presence. And then we also gathered qualitative feedback about each of those questions. So go through the findings real quick. We basically found that the VR and AR users both found the virtual replicas useful and aided in the efficiency and effectiveness of their communication and prototyping. On the AR side, the participants found that the presence of the remote guest was improved with the system. We found that a key contributing factor was that the AR user could see the VR user's avatar translated to where they were actually working, allowing them to be aware of what the other user was actually doing and what they were interacting with. And on the VR side, users found VirtualNexus provided a sense of physical presence, and in particular, when the annotations and object reacted to the remote environment physically. The VR participants also found the environment cutouts to be intuitive and effective to use. Some of them pointed out that the cutouts can be pulled closer to provide better precision, which is exactly our design goal with the system. All right, so in future work, we'll plan to investigate the interactive modalities if we want to scale to more users, so more users on either the AR or the VR side. And we also plan to address one misalignment, which is that the AR user sees the VR user moving, but the VR user doesn't see the AR user moving, right? Because they've got the background video. So this is something that with, for example, redirected gaze rendering, we can address in future work. And finally, we'll be looking at using neural rendering to provide a more unified experience with all of the different rendering all in a single system. Okay, so to sum up, VirtualNexus enables coherent interactions between high-fidelity 360 video and depth-based reconstruction, so we can get the best of both worlds without needed context switch in a nice and very intuitive way. Environment cutouts provide both interactivity and mobility for the VR user in one very easy-to-use interactive technique. And finally, the physical object digitization provides more efficient communication and rapid prototyping. And with that, I'll conclude. Any questions?
Steve Feiner, Columbia University. Great work. I have a question about the cutouts. So you showed the remote VR user making a cutout of a whiteboard, getting closer to it, and then the AR user can see the representation of the VR user getting closer to that whiteboard. Now, you also had another cutout where the VR user had created a graph, I think, and put it on a desk. And let's say the desk is like way over here in the room and the whiteboard's way over there, and now our VR user has 2 cutouts and wants to do something on the whiteboard and then do something on the desk. And does the AR user see them like running from one side to the other or rematerializing and dematerializing? How does that work?
That is a fantastic question. So the answer is, in the current setup, you can only have one cutout at a time. So okay. What the current setup would allow is for you to push the cutout back and then pull another one out. Right. So we can store the cutouts potentially, have you kind of move one and move the other, so you kind of still have to move a little bit manually. This is an interesting question. Yes. Like, how do you represent it? If we really did want to have somebody bring multiple parts of the space together, how do we represent that? That's a very good question, and it's something we'll look at in future.
A good thing to look at.
Yeah.
Thank you.
So I had Ari Blenkhorn, Johns Hopkins Applied Physics Lab. So I had a 2-part question, but Steve just took the first part. The follow-up is, you were showing the remote user doing a cutout of the whiteboard, and in that case, as they move toward it, it's pretty obvious to the AR user what is attracting their interest. But in cases where they're cutting out something that's a less obvious part of their environment, is there any feedback to the AR user, and do you think that would be helpful?
Yeah, that's actually a really fantastic question. I suspect that during the travel, it may not be immediately obvious, but then it's not always obvious in the real world where you're walking towards, right, if there's not an obvious destination. But at the end point of that destination, when the user's brought everything close enough to their kind of arm's reach, it should be pretty clear what they're interacting with. And you also see their hands, so you know what they're actually working with. Yeah.
Okay, thank you.
Thank you for the questions. Thank you.